Okay, continuing on with our acid and base discussion. There are some substances that can act as both an acid or a base, particularly again, when we come to the Bronsted-Lowry definition. And if you'll start to notice, we're using that definition the most, and that really is the one, when you talk about acids and bases, that's the definition that most people are referring to when they talk about just generally acids and bases. It's the Bronsted-Lowry definition. So as a refresher, a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. So when the Bronsted-Lowry definition of an acid is very similar to maybe the Arrhenius definition. It donates a proton, it donates a hydrogen ion. But the Bronsted base is different, and it doesn't have anything to do with the hydroxide ion. It has to do with its ability to accept a hydrogen ion, or sometimes short-term called a proton. Okay. Now, and there was a refresher, why can we use the hydrogen ion interchangeably with the word proton? The hydrogen ion has a positive charge. Now remember, going back to the basics of our chemistry towards the beginning of the school year, hydrogen is the very first element on the periodic table. Its atomic number is 1. That means it has 1 proton. When it's in its neutral state, it also has 1 electron. When it becomes an ion, it has donated its electron most of the time to something else to form a bond. Now, if it's an ionic bond, it's donating its proton generally with a metal or another polyatomic ion. It's donating that proton and becoming positively charged. Or excuse me, it's donating that electron. It's donating its electron, so it becomes positively charged. Well, the only thing left in that hydrogen ion then, if it donates 1 electron, the only thing that's left over is a proton. So we can call a hydrogen ion a proton, and it means the same thing. It's a proton because that's the only thing left inside of it. It's donated its electron to something else. All right, that's how we use that interchangeably. So sometimes I and other people will say proton, a proton donor. Sometimes you'll hear hydrogen ion donor and hydrogen ion acceptor, but it's the same thing because it's just that kick out of the electron from hydrogen, just leaving that 1 proton. All right, so the term amphoteric, this AMPH prefix here should look familiar to you. Maybe not the word amphoteric, but you have certainly seen this word, this prefix before. Think of the animals and amphibians. Why are amphibians called amphibians? Well, hopefully you know that they're called amphibians because they live on both land, or at least part of their life in land and part of their life in water. They go back and forth, land, water, okay? The same idea is with these acids and bases. They can act as either. So an amphoteric substance can sometimes, depending on what it's reacting with, act like a base, and sometimes it can act like an acid. So that's what an amphoteric substance is. A couple of examples. Water would be one. Another one, which I've shown you here, is hydrogen carbonate. So the hydrogen carbonate ion, if it reacts, and this is all on page, let me tell you the page, because you can read it. You know, there's a water example also on page 421. So in this particular case, so on page 421 in your textbook, if you want to go grab that, pause the video, go get your book if you don't have it nearby. So if we take this hydrogen carbonate ion, negatively charged, react it with a hydronium ion, look what happens. You form H2CO3 and water. And look at the transition here. HCO3 minus has accepted a proton from the hydronium ion to become neutral and have an extra hydrogen. And this reaction creates H2CO3 and water. Okay? So in this particular case, HCO3 minus accepts the proton. So in this particular example, it's acting like a base because we've reacted it with hydronium. But let's take the same, so same, but instead of reacting it with a hydronium ion, we're going to react it with a hydroxide ion. And look what happens. HCO3 minus donates a proton to OH minus to create a carbonate ion and water. So in this case, HCO3 minus was a proton donor, so it's acting as an acid when it reacts with OH minus. So an amphoteric substance, it just depends on what it's reacting with, and it can go either way depending on what the other reactant is and how it would choose to interact with that other reactant. So amphoteric substance can be Lewis bases, Bronsted-Lowry acids, or Bronsted-Lowry bases, and they act differently depending on what else they're reacting with. Now, another a type of acids we need to talk about are polyprotic. And again, let's look at this prefix poly. It means many. All right, so what that means, it has many, or more than one anyway, proton that it might want to donate. All right, so let's clear out these definitions. All right, monoprotic means it can only donate one proton. So like HCl, there's only one available hydrogen there to even discuss. So that's the only way, that's the only thing that can get donated. It only has one, monoprotic. Polyprotic, you typically have either under that umbrella of polyprotic acids, you'll either have a diprotic or a triprotic. Those prefixes tell you exactly what that means. So a diprotic acid would have two hydrogens that it could potentially donate, and the triprotic could possibly donate those three. Okay, all the same molecule, but has multiple protons that it could potentially donate. So how does that all interact? Well, remember the idea of Ka and Kb, and that Ka of a substance times its Kb, the ionization constant for the acid, times the ionization constant from the base, and you multiply them together, you get the Kw. Remember that, which is 1 times 10 to the negative 14. So when you have a polyprotic acid, you have multiple ionization constants because it takes a certain amount or a certain ability or a certain concentration of that first proton will go, and then you'll have another proton that will eventually be released as well. The way this works is, though, the more protons you have to donate, the harder it gets to donate the remaining. So in the example, if we go back and look at this example right here, this reaction in reverse. So let's look at that. So H2CO3 reacts with water. Oh, let me get the arrows in here. Sorry about that. Okay, so in this reaction, equilibrium reaction, you can see the H2CO3 has these two hydrogen ions that in theory it could ionize in water. Well, when that first one goes, you lose the one and you create HC3O minus and H3O plus when it's reacting with water. Now remember, water is a liquid, so when you're figuring out the Ka, that equation, it does not have to go on the denominator because it's a liquid, it's just one. So our Ka expression would be the products, HCO3, and this would also be aqueous. Let me fix that. Okay, so you'd have HCO3 minus in the hydronium ion on your numerator. That's going to be divided by, we can ignore water because it's a pure substance, H2CO3 minus, H2CO3. When we do that, you'll get this constant, 4.3 times 10 to the negative 7. Now let's compare that with the second ionization constant, because now we still have this one that could get donated. So when we do that in water, we create a carbonate ion and more hydronium ions. When we look at the second association, acid dissociation constant, the Ka2, we get carbonate as a product hydronium as a product, and then HCO3 minus as the reactant. Water as a liquid does not have to be included, but look at the change. Ka1 is much greater than Ka2. Look at the difference in exponents there. You went from -7 all the way down to -11. So one other note on this before I close out this particular session on our discussion on polyprotic acids is that all polyprotic acids have at least one amphoteric substance in their series of ionizations. So that there's going to be one substance as you look at these polyprotic acids that can act as either an acid or a base. Now, lastly, we're going to talk about pH indicators. These are substances that change color depending on the pH, and they have a range of colors. And we talked about that a little bit with litmus. Litmus is typically a very easy, cheap acid-base indicator, and it's very stable. You can put it on paper and it'll last a really long time, and so we'll use pH paper in the lab a lot. It doesn't give you exact numbers. It's more like a range and a general idea of whether it's acidic or basic. So here in your textbook too, the chart looks a little bit different. But in your textbook on page 423, you'll have two similar charts. You'll have this kind of chart. It's at the top. It's flipped sideways, but it deals with most of the same substances. And you'll see all these various chemical indicators: methyl violet, thymol blue, methyl yellow, bromophenol blue, methyl orange, methyl red. There's litmus that we've talked about already, bromothymol blue, phenol red, and on and on and on. So you can see that litmus is like a purplish blue to pinkish red. Okay, so an acid, so here's the pH level of 7. So with litmus, anything pink or red is an acid. As it turns blue or to purple, it's indicating a base. So these are all ranges. So if you look here at methyl violet, it's not as easily, and also just as an FYI, these right here are a little easier to use than some of these others because the dividing line is generally around a pH of 7. So at the neutral point is where you start to see that transition. But look with methyl violet and thymol blue and bromophenol blue, it's much lower. That transition point is a much lower pH. So it tells you if it's a strong acid maybe or not, but after that, it's a little confusing as to whether or not it's still an acid or a base because the transition is well below the pH of 7. And likewise, these guys over here, the transition point is basic. So it doesn't tell you as much information about whether or not it's an acid or a base. It just tells you whether it's it's a more basic base based on the higher pH levels at the transition point of their color change. But again, these indicators are rough estimates. Like you're not going to be able to get an exact pH even using litmus paper because there's not a huge shift in these colorings at all. So it's an estimate, oh, it's an acid, oh, it's a base. Sometimes depending, you'll get a little bit more specific and you can see if it's a slightly stronger acid or a slightly stronger base, but the specificity would be lacking. And these are generally called universal indicators. But down here, if you look on and also on the bottom of page 4, the graphic that's on the kind of towards the bottom of your page 423 in your textbook, these are naturally occurring indicators, typically in plants and vegetables. And you can see how those would work. Beets, it looks very similar to litmus in a way, that red to purplish blue transition. But you've got blueberries, cherries, curry powder, very interesting. All of these various substances that are found naturally can also be used as indicators. There's also an instrument that has become more widely used as technology has grown, and that's a pH meter. And if you look at the image on page 424, you will see the pH meter, and it is much more accurate. So it actually gives you a readout. So if you were to put your if you had a pH probe, you could put your probe into your orange juice, for example, or into lemon juice, and you would see lemon juice is extremely acidic. You'd probably get around a 2-ish reading on that. Extremely acidic. If you put in orange juice, you have the citric acid, which is much less acidic than, say, the lemon juice that you stuck your pH meter in. But it gives you a very accurate reading. So it depends on what you need in a lab. If you need something and you need to know the exact pH, you cannot use these indicators. It doesn't tell you. If you just need to know whether something is more of a stronger acid or a weaker acid, or a stronger base or a weaker base, just a general knowledge, the indicators are good. But you do not want to use them for exact measurement. You need a pH meter for that. All right, that wraps it up for today. We will check back in tomorrow. Make sure you look for the questions I want you to answer. Hope you guys are doing well, and I will hopefully see you soon.